What you know is that TCP, we have one type of segment. It contains the source and destination port numbers, where the port numbers identify the applications communicating. It also contains a sequence number. The sequence number indicates the order of the data that's contained within this segment. So if the TCP segment contains data, it doesn't have to. This data could be empty. It could be 0 bytes. But if it does, then the sequence number is significant, and it indicates the order of this data in the set of data that's come from the application. We'll see some more examples of that shortly. Sometimes the segment can have multiple meanings, and those meanings are determined by the flags. When a flag is set, then that segment has some additional meaning than just carrying data. For example, the ACK flag, when that's set to 1, it means this segment also is an acknowledgement for some data that's been received. And the acknowledgement number is significant in that case. And the acknowledgement numbers work in the same way that we've seen all through this course. That is, if I send data with sequence number 1, then the receiver would send back an acknowledgement saying, thank you, I now expect number 2. So the acknowledgement number would be 2. That is one more than what was received. And there are some other fields in here that are used for different mechanisms. Sequence numbers are 32-bit numbers. They're used to keep track of the order of the data that's sent. We must deliver the data in order from the source to destination. And they're used for error, flow, and congestion control. Before we transfer data, we establish a connection. And the way that TCP establishes a connection is through a three-way handshake. These are the 3 messages that illustrate that. The source, or the client that wants to initiate a connection, sends a TCP segment. This is a special TCP segment. It doesn't contain data. The SYN flag is set because the purpose of this segment is to synchronize sequence numbers. So the SYN flag is set. The sequence number field is set to an initial sequence number that the client chooses. It chooses a value. It doesn't have to be 0. It's the number that it wants to start with, the initial sequence number. A tells B its chosen initial sequence number. B does the same, because in TCP, once we establish a connection, both sides can transfer data. A can be sending data to B, B can be sending data to A. And independent, that is, the sequence number used in both directions are different or can be different. They don't depend on each other. A sends data to B, and at the same time B sends data to A. There's nothing to stop that. It's over a network. So your computer process, if you've got data to send, you transmit it, and then data arrives from the other source, then you process that. So there's nothing to stop from sending and receiving at the same time. Of course, your computer only does one thing at the one time. That is, your CPU is either processing the data to send or processing the data to receive. So they happen sequentially, but effectively we can send and receive data at the same time.
How many bits? How many bits?
Flag is 1 bit.
1 bit, and how they know that which bit is in or?
It's specified. I don't think we've shown it here. These are the flags. I think it's in this order. The first bit is for this flag, the second bit, third, fourth, fifth, and so on.
And how many space for bit?
8 bits, from 8 to 16, 8
so
bits.
We have 6 space. One happens in which position is that?
Yeah, so we have 8 bits. Here we have 8 different flags.
Okay.
If the first bit is set, then this flag is on. If the fourth bit is set, then the ACK flag is on.
So when the flag is SYN, we can say that SYN equal to 1.
Yes, when the seventh bit is 1, that means this is a SYN segment. The meaning of this segment is to synchronize sequence numbers. A tells B its initial sequence number. B tells A its initial sequence number. B also acknowledges the initial sequence number that A chose. So when B receives this, it says, thank you. The first piece of data I expect is your initial sequence number plus 1. If A chooses initial sequence number of 10, acknowledgement number here would be 11. And finally, A acknowledges B's chosen initial sequence number. So at the end of these three messages being exchanged, A and B know each other's initial sequence numbers, and importantly, they know that the other has agreed upon using these numbers. That's the purpose of the connection set up here, to synchronize sequence numbers. Then we start sending data. We can close a connection after we send data. We won't go through the details, but there's some steps of finishing, send a segment with the FIN flag to true, and then get an acknowledgement of that. There's some other operations that you can abort a connection using a different reset flag. One thing that is a little bit unique to TCP is that you can have a half-open connection. Remember, A and B can send data in both directions. What can happen is when A has no more data to send, it closes the connection, FIN and an ACK. Therefore, A will not send any more data in this connection. But B can keep sending data to A. That would be a half-open or half-closed connection because it's closed from one endpoint's perspective, but data can keep flowing in the other direction. So the connection is not fully closed until both sides close the connection. That is, both sides initiate this finish sequence. And then the connection's closed, no more data is going to be transferred. It's a little bit more complex than this in that after there might be some timeout phases to make sure the connection is really closed. And there are some other cases that we will not cover. You need to go into a lot more detail of connection establishment and closing to see all the details. So let's focus now on data transfer. After we open a connection, how do we transfer data? TCP uses a sliding window mechanism. So we've seen sliding window mechanisms where the source can send a set of segments before it has to wait for an ACK. It increases the efficiency of the data transfer. TCP specifies different algorithms for error, flow, and congestion control. We'll see some algorithms for error control shortly. Some of the details of these algorithms depend upon the implementation. That is, there's a standard for TCP, a document that says this is what TCP should do. If you want to implement TCP, you must follow that standard. But some things are undefined, and therefore an implementation on a Linux operating system, which has one implementation of TCP, may be different than an implementation on a Windows operating system. So some parts may differ depending upon who implemented it. For example, and we'll see some example, when to send data, when to send an acknowledgement. We'll see some examples of different options that TCP doesn't specify exactly how to do it. It's up to the implementer to choose. TCP is a stream-oriented data transfer service. The application wants to transfer data across the internet. The application generates some data, sends it to TCP, and we can think that the application generates a message that it wants to send, sends to TCP. TCP doesn't treat this as a message, it just treats it as a sequence or a stream of bytes. And we can see it may break that message up and send it as multiple segments. Or it may not send that message just yet. It may wait for another message from the application and send both messages in one segment. So TCP doesn't care that the application may be sending messages. It just thinks of those messages as a sequence of bytes, a stream of bytes. Let's see how that works. Here's an example where our application initially generates 10,000 bytes of data. The diagram I'm going to draw on the board is similar to, or almost identical to this diagram. I'm going to just draw it on the board as we go through this example. A wants to send some data to B. A connection has been established. The initial sequence number chosen by A in this example was, I think, specified 300, just in this example. B also chose an initial sequence number. We don't care in this example because we're only looking at the data going from A to B. The application at computer A generates some data. 10,000 bytes of data it wants to send. I'll draw it like this. That is, if this is TCP, or the software implementing TCP on computer A, the application generates some data and sends that inside the computer to the TCP software. For example, someone has opened an application, they've loaded in a 10,000 byte file that they want to transfer, and they've clicked the send button. That triggers that data to be sent to TCP, and now TCP goes to work to try to deliver it across the internet. Let's go through an example to see how we treat sequence numbers when we deliver that data. 10,000 bytes from TCP's perspective. We could number those bytes, the first byte up to the last byte, byte number 10,000. Since the initial sequence number was 300, remember with a connection establishment, A tells B the initial sequence number of 300, B sends back an ACK saying I expect 301. So in fact the first byte of data that A is going to send we can think has sequence number 301. And each byte corresponds to a sequence number. Therefore the last byte here, the 10,000th byte, would have sequence number 10,300. So remember, that's what's different from what we've seen in other protocols. In other protocols, each frame had a sequence number. Frame 1, frame 2, frame 3. In TCP, each byte has a sequence number. Byte 301, 302, up to byte 10,300. So we have 10,000 bytes of data to send. TCP then makes a decision, how is it going to send that data as segments across the internet? And this is what is implementation dependent. It depends upon the different algorithms and some performance trade-offs that the implementation has made. It may choose to divide that up into multiple segments. 10,000 bytes, maybe we divide it into 10 1,000 byte segments. Or one 1,000 byte segment, one 3,000 and one 6,000. Or in this example, one 1,000 byte, one 1,000 and another two of 4,000. This is just an example. How do we know how it divides it up? It's very hard to predict without knowing the details of the individual algorithms: error control, flow control, congestion control. Each of those algorithms have an impact upon how TCP would split that data up. So at this stage we don't know. And the maximum transmission unit, that is what's the maximum size of the frame that we can send as well. So there are different factors that will determine how this 10,000 bytes is split into segments. Let's just go through one example where I've chosen some numbers just to make it easy to illustrate. It decides in this case to split into 4 segments of 1,000 bytes and 4,000 bytes. We could draw those segments. Remember, we said that the first byte was 301. The last one would be 10,300. If we divide it up into these 4 segments, then what's the first byte, or what's the last byte of the first segment? 1,300. If you start counting at 301 and you increment 1,000 times, you get to 1,300. That's the last byte of the first segment. Therefore, the first byte of the second segment would be 1,301. And so on. The first byte of this segment would be 2301. And here, 6301. We'll use those numbers in a moment. So that's just if we order those bytes, then know that if we then decide to divide it in this way, then they are the first bytes of each of those 4 segments. So what TCP does is it creates 4 different segments. So it takes those 4 chunks of data, attaches a header to each, a TCP header, and it's going to send those 4 segments across the internet. So that's shown here. The 4 chunks of data attach the header, H, and in the header we set all the fields to the appropriate values. One of the fields is the sequence number. The sequence number in the header is set to the sequence number of the first byte of data contained in that segment. So in the first segment, the header would have a sequence number and the value would be 301. In the second segment, the value would be 1,301, 2,301 and 6,301.
This number will be the first operator or the first operator?
This is it's counting data only. The header, one of the fields in the header is the sequence number. If we go back to the header, somewhere, this field. So here's our data. Of course, another way to draw this segment is data and the header. And the header contains multiple fields, the ones specified here. The data contains this. That is, this data is put into here. The header has these fields, and the values are set, the appropriate values, like the source port number identifies the source application, destination port number, and importantly, the sequence number field is set to SN, set to the sequence number of the first byte of this data. And same with the next 3 segments. The second segment, we also attach a header. We have 1,000 bytes. And the first byte is 1301. Therefore, in the header, the sequence number field would be set to 1,301. And for the third segment and the fourth segment. So we'd set the header sequence number fields to these 4 values. And set the other fields to the appropriate values. TCP then takes these segments one at a time and sends the first one to IP. This is all inside computer A. The application generated 10,000 bytes, sent it to TCP. TCP divided it into 4 chunks, creates 4 segments, sends the first segment to the internet protocol inside the computer, which will eventually process it and send it out of the computer. The second segment would be sent to the internet protocol, processed and sent out of the computer, third and the fourth segment. Those 4 segments sent one at a time across the internet. Send segment 1, 2, 3, then 4. Of course, IP would add the appropriate destination address and so on. So that's how sequence numbers are used in TCP. They identify the bytes, and the header contains the value of the first byte in the data. So we could draw that. If this is the data that segment that we're transmitting across the internet, it's a TCP segment. I'll just indicate that it contains data. It contains a sequence number of 301. It contains other fields in the header, and they have values. I'm just not going to write all the values of the header here. So just to summarise the main points, this segment contains some data and a sequence number of 301. We know it contains 1,000 bytes, so I'll just write that here as well. When B receives that, in this example, B is going to acknowledge, send back an acknowledgement. And the acknowledgement is just a TCP segment. In this case, B has no data to send to A. So it's in fact a TCP segment with no data. The length of the data is 0. But importantly, the ACK flag is set. So I'll denote this as an ACK. And the acknowledgement number is what value? The acknowledgements indicate the next byte expected. So let's look from the perspective of B. When it receives this segment, it knew that the initial sequence number of A was 300. Therefore, when it receives some data, it's expecting to receive sequence number 301. That's what it expects. It does receive sequence number 301. And it in fact receives 1,000 bytes. It knows how much data is in the segment that it receives. So from B's perspective, it's received sequence number 301 up to 1,300. Therefore, it sends back an ACK saying, thank you, I now expect 1301, which is just the TCP segment with the acknowledgement number set to 1301. And in this example, A then sends the second segment. It contains some data. It contains the sequence number 2301. When B receives that, B has now received, what did I say, 2301? 1301. I'm glad you're awake. It receives sequence number 1301, that's this second segment here, and it contains 1,000 bytes, so it's really sequence numbers 1301 up to 2,300 have been received by B. Therefore, it sends back an ACK saying, I expect 2,301. And we get this if we keep going. Note that all I'm drawing here is TCP segments, but I'm giving some names to them to indicate what they're meaning. This contains data and a sequence number. The ACK flag is set, and it contains an ACK number.
This is not the three-way handshaking. The three-way handshaking used for the connection is the bit.
The three-way handshake has already happened in this example. It happened up here.
Okay. And
We haven't drawn it.
This when we transmit, we use sliding control like this.
This is one example of the transmission of data. We can use sliding window. In this case, we only have a window to allow us to send one segment. This is a very simple case. We'll show you a different one in a moment. At the end, B has received sequence number 301 up until 10,300. If we follow this approach, 301, the third segment would be up to 6,300 and the fourth one up to 10,300. If we continue our scenario, so that first 10,000 bytes, the user opened their application, press send to send the 10,000 bytes to the destination. TCP used this approach to send it as 4 segments. Sometime later, the user opens up or using the application, loads in a 20,000 byte file and presses send. That is, they want to send more data to the destination. Then we just continue on using those sequence numbers. Within the same connection, A will decide to divide that into multiple segments in different sizes potentially. What's the first sequence number?
Up to you.
No, it's not.
Because we want to do ISNA.
No, this is continuing the data.
Continue form.
Our connection is still open.
Okay. 10301.
We continue on from here. That is, from TCP's perspective, this second piece of data, this second message from the application, is a continuation of the first one. It's just another 20,000 bytes. So it'd start from 10,300, 10,301, divide into segments and keep transmitting. So within one connection, we just keep using those sequence numbers. And that connection may be open for minutes, hours, possibly days, depending upon whether they're still transferring data. So TCP does not distinguish that this is the first message of 10,000 bytes and that's the second message of 20,000 bytes. It just treats it all as a sequence or a stream of 30,000 bytes. It doesn't care whether they're two different messages. Potentially what it could do is something slightly different, is that if this was small, maybe this was 100 bytes, it receives it, saves that 100 bytes, doesn't send anything, and then shortly later A sends 200 bytes, the application. TCP may decide to send all 300 bytes in one segment. So join the two messages together and send them in one segment. So there's nothing to stop that from happening. And therefore B would receive all 300 bytes at once. Why do we start at 301? Because A chose an initial sequence number of 300. That's just an example. In a different case, it may choose 7,462. It chooses based on what it's done in the past, but think at the start of the connection it chooses an initial sequence number which could be random from our perspective. It's not random, it's a more complex way to choose it, but it can be any value. It's just once we have an initial sequence number, all bytes after that follow that. Instead of starting at 0, we can start at a non-zero value. What the real purpose is, we open a connection, this time we use 300, and maybe we go up to 30,300. We close the connection. Next time we open a connection, we may choose an initial sequence number of 30,301, more than what we used in the last connection. That's one way to implement that.
TCP have to be ordered, or have to be ordered.
TCP must make sure that the data you send arrives at the destination in order. If you have a 1 megabyte email that you want to send and you send it, and the application at B receives that 1 megabytes, but it's all out of order, you will not be able to read the email. The data must be delivered in order.
When we send across the internet, maybe the packet arrive not in the sequence.
So we need some form of error control and some reordering to put them back into sequence. We'll see an example of error control, what may happen. Yep.
Well, for this one, you said that the TCP header must be included with data, and then when it passes through the IP layer, does it have to include more layer from the IP header?
Yes, we've only shown what TCP does. TCP creates a TCP segment, contains data and a header, sends it to the IP software in your computer, adds an IP header, sends it to your LAN card, adds an Ethernet header, adds the physical layer bits, transmits it as a signal, and then as it's processed, the headers are processed and transmitted.
Or header at each level, will it keep going on and it has more header?
Yes, in our protocol architecture, we can think every protocol layer adds a header, potentially adds a header. Some add a trailer as well. One more example before we move on to error control. Oh, there they are. Here we had a very simple transfer of data act, data act, data act, like stop and wait. Doesn't have to be like that. Remember, we can use a sliding window. It could have been more like this. That is, with a sliding window, we're allowed to send a set of segments, transmit them before we have to wait for an ACK. Then the ACKs come back. It could have been more like this. Instead of having to wait for an ACK before sending the second segment, send the 4 segments and then wait for the ACKs. The same numbers would be here. Data 301. This would be ACK 1301. Data 1301, 2301, 6301. Same numbers on here. So this is the sliding or the window mechanism in use. We're allowed to send multiple segments. Or it could have been like this. The receiver may have decided, let's not send an ACK for every segment received. Let's be a little bit more efficient and let's maybe send an ACK for every second segment. That is, you receive the first segment, wait before you send an ACK. If you receive more, then send an ACK after the second segment. So the data values would be the same, 301, 1301, 2301, 6301. What is the value of this ACK? What is the acknowledgement number in that first ACK there? 2301. From B's perspective, it's received the first segment ranging from 301 up to 1300, and the second segment ranging from 1301 up to 2300. So it's received bytes 301 up to 2300 in order. Everything's okay. Therefore sends back one ACK saying I expect 2301. That's the next sequence number expected. That's if we act after the second segment, not each segment. And similar, the last one would be ACK, what value? 10301. We receive the third segment, then the fourth segment. We've now received all 10,000 bytes from 301 up to 10,300. The next expected will be 10,301. Three different scenarios that may arise, all valid scenarios in TCP. Which one happens? It depends on many factors, of the timing of how long it takes to transmit this data, the algorithms used at the source and destination, the implementations. At this stage, with the knowledge we have at TCP, we cannot predict which one would happen. Any of them are valid. So this ACK here we'd call a cumulative ACK. It acks two segments. It accumulates up the data it's received and acks all of the data received so far. So it doesn't have to be for every two segments, it could be for a set of segments, more than two.
How the ACK know that the fragment size, they know by header or know by, they have to count the byte received?
If you look back in the structure of the header,
Size, we have the
we can determine the size of the data.
So they know from the header and they can predict the next fragment.
Not predict.
Not predict, they know.
They know.
They
Yeah.
know that the next packet will start with which number.
Yes. If you receive sequence number 301 and it contains 1,000 bytes,
Inside the O1, they tell that this data is 1,000 bytes, and the next they calculate the next one.
calculate the next must be 1,301.
Okay.
Yeah. You know the length of the data because you've just received it.
So they trust the header, not necessarily to count the byte actually received.
No, it receives an IP datagram. It knows how many bytes are in there because when it removes it knows the length of the header and it knows how many bytes it received. If the header is 20 bytes and we've received 1,020, the data must be 1,000 bytes. So it can count the length of the data. Any other questions about sequence numbers? The next part is what happens when we lose data. Before we do that, quiz not yet. We still have to finish TCP. So that's the ideal case where all the data gets to the destination. Let's look at a simple case where what happens if some of the data doesn't get to the destination, if we lose some data. How does TCP implement error control? TCP uses a selective retransmission ARQ scheme. Remember, we went through three approaches: stop and wait, go back N, and selective reject or selective retransmission. Stop and wait, we just send one, receive an ACK, send, receive an ACK. If we don't receive the ACK, we retransmit. With go back N, we could send multiple data segments and we wait for the ACK. If we notice something's missing, we retransmit we go back and retransmit the n segments from the one that was missing. In selective reject or selective retransmission, we send a set of segments. If we notice one of them is missing, then we'll retransmit just that one. We retransmit just one. For this to work, the receiver needs some buffers to store the segments that have been received out of order. We'll see that in our example. We know this, the ACK numbers indicate the next in order sequence number expected. We must receive the data in order. When we send an ACK, we say what's the next one expected in order. We will not ACK out of order data. If a data segment sent is not ACKed within some timeout period, the source will retransmit. So that's our basic retransmission scheme. Send some data, wait for an ACK. If you don't receive an ACK, send that data again. We may use cumulative ACKs like we used here. And later we'll go through some optimization of this. But first let's go through the basic retransmission scheme of TCP. In this example, we're going to keep something simple. All the data have 1,000 bytes. Well, each segment contains 1,000 bytes of data, just in this example. A initially has 6,000 bytes to send, and it's going to send them as 6 segments. So we'll see host A wants to send some data to B, and it's got 6,000 bytes. It's going to send them as 6 1,000 byte segments. Our initial sequence number was 0, chosen by A. Therefore, the first sequence number of the first segment will be 1. And if this is the 6 segments being transmitted, we have a data segment with sequence number 1. The next one will be 1,001, 2,001, 3,001, 5,001. So that would be our 6 segments transmitted by A. When A transmits a segment, it starts a timer for that segment. And it's going to wait for an ACK. If it doesn't receive an ACK within this timeout period, it will retransmit that segment. So here A transmits the 6 segments, one after another. It's going to, in this scenario, one of those segments is not going to arrive at the destination. It's going to be lost. And we'll see how TCP deals with that. So B receives the first segment. Let's keep track of the data that B has received. We'll keep track of it in terms of sequence numbers. When B receives the first segment, it successfully received data from sequence number 1 up until 1,000. Each segment contains 1,000 bytes. First segment, sequence number 1, when it's received, B has received the first 1,000 bytes, 1 to 1,000. So everything's okay from B's perspective. Because the initial sequence number was 0, then this is expected. If the initial sequence number is 0, the first piece of data expected should be 1. So that's okay. Then shortly later, B receives the second segment. No, before that, in this case, B is going to ACK every segment that it receives. So when it receives the first segment, it sends an ACK. I've received 1 up to 1,000. The ACK number is going to be 1,001. saying I now expect to receive sequence number 1001. When it receives the second segment, sequence number 1001, it's received sequence number 1001 up until 2000.
The ISSA 0 includes for established connection and the 1 is for data.
Again, we haven't shown it in this example. Before all this, there was a connection establishment. There was a three-way handshake up here. I've assumed that happened. In the three-way handshake, A chose initial sequence number 0. That's the normal.
The data is the next plus 1.
Plus 1, because if A chooses initial sequence number 0, B responds with an ACK with the value of 1, saying I expect to receive sequence number 1. And we send sequence number 1.
And if for handshaking, we have to send 0 for SYN 0.
In this example, we would have sent a SYN segment and their sequence number would have been 0, indicating the initial sequence number chosen by A was 0.
So an ACK is 1.
And the
For the data,
ACK would be 1.
1.
Yep. The ACK number would be 1. So I haven't shown that here. After B receives the second segment, it sends back an ACK. B has now received bytes 1 up to 2000. It sends an ACK with ACK number 2001. So this is normal. Send an ACK saying what's the next byte expected. From B's perspective, the next thing that happens is it receives the segment containing data 3001 up to 4000. So this is from B's perspective. This is a problem. B previously sent an ACK saying I expect to receive 2001. It receives a segment starting from 3001 going up to 4000. Where's 2001? So what B does in this case, it sends an ACK, but when we send an ACK, we always acknowledge the sequence numbers in order. We've received 1 up to 2000. We buffer this data. That is, we store this 1000 bytes in memory in a buffer, and we send back an ACK saying, I expect to receive 2001. We must receive the data in order. When B receives the next segment, 4001, again, it was expecting 2001. It's received something out of order. So it buffers that, puts it in memory, and sends back an ACK saying, I'm still expecting to receive 2001. And the same happens with the last segment. So with TCP, the receiver needs some buffer space to store these segments, this data, 3000 bytes in this case. Sends back ACKs, and then B has sent those 3 ACKs and is waiting for more data to be received. In the meantime, at host A, remember, after transmitting a data segment, you start a timer and you wait for an ACK for that data segment. When we sent the first segment, we started a timer. Let's say it's a long timeout period. We received an ACK for that first segment because we sent the first segment from sequence numbers 1 up to 1000. We receive an ACK with ACK number 1001 that acknowledges the first segment. This first ACK indicates the first data segment has been received successfully. So when we receive an ACK, we stop the timer and that data has been successfully received. Move on to the next piece. So we receive an ACK for the second segment here. So that's okay. And then from A's perspective, we receive an ACK, but we know that this ACK is still asking for sequence number 2001. So we haven't had our segment 3 acknowledged yet. Segment 3 contained sequence number 2001, but this ACK says B is still expecting 2001. That means B has not received 2001 yet. And same with this ACK and this ACK. So A is still waiting for an ACK for its third segment. It's waiting, it's waiting, it's waiting, and then a timeout occurs. The timer was started when we sent this segment. The timeout interval is predefined, some value is defined for TCP. When the timer expires, that triggers A to retransmit that segment. So we retransmit segment with sequence number 2001 up to 3000. It's successfully received. When B receives that segment, it contains sequence numbers 2001 up to 3000. So now, from B's perspective, we've received the first 3 segments. We've got the next 3 in the buffer, stored in memory. So in fact, we've received sequence numbers 1 in order up until 6000. So we've received all 6000 bytes. Therefore, we send back an ACK saying, I now expect to receive 6001. And we can move on to the next data if there's more data. Yeah?
The ISMB is for like what sequence that we send data to A, right?
Yes, ISMB just for data coming from B.
What happens if B not send any data to A, just like one side?
In this case, B is not sending any data.
Yeah, what the ISMB
At the connection setup, which happened before all of this, A chose ISN A of 0. Let's say B chose ISN B of 10,000, some other number. B is not sending any data, and therefore it's not increasing that sequence number.
So just any number?
Any number independent, and they're independent. ISN A is used just for data from A to B, ISN B just for B to A. And in this case, there's no data from B to A. Everyone can answer a quiz question on how TCP basic retransmission works?
Maybe. Now?
Maybe. After we go through the next one. We have one more.
This one?
Next one. There's a next one. So the basic mechanism, we transmit our data segments, we wait for an ACK. If we don't receive an ACK within a timeout period, we retransmit. That's normal, we've seen this before. When B receives data, it acknowledges the next in-order sequence number expected. If we receive data out of order, we still expect 2001, 2001, 2001. Once we've received all data and we can put it back into order, we can acknowledge the next number. 6001 is the next number. We need enough buffer at the receiver to store these out of order segments. And it's related to the window size. So what's the size of the buffer? When we talked about flow control, the window size limits how much A could send so that we don't overflow the buffer. How long should our timer be, or our timeout interval? typical quiz question. How long is our timeout interval, or how would you calculate it? What's the optimal value of our timeout interval? How would you calculate it? Transmission time, propagation. So the timeout interval should be large enough such that we give B a chance to send an ACK back. That is, large enough so that we include the time to transmit the data, B to process it, and to get the ACK back. So just slightly larger than that time. If we make it too large, then what happens is that we spend a lot of time waiting if we lose data. Let's say it wasn't here, but it was all the way down here. A would send at 6, waiting for the timeout, waiting, and then retransmit. If the timeout interval is too large, we'll be inefficient if we lose data. So we usually have it just larger than the typical time it takes to send and receive the ACK. How long does it take for my computer to send and receive an ACK if I communicate with this computer? Approximately. Microseconds, maybe a millisecond or two. Microseconds, because the transmission time and the propagation time is quite small. How long does it take for my computer to send to the Facebook web server in the US? Milliseconds, tens of milliseconds, hundreds of milliseconds in some cases. Today it may be 100 milliseconds, tomorrow it may be 50 milliseconds to the same destination because of different traffic in the internet. It's very hard to predict what the typical time is. And that typical time may change a lot, it varies a lot. Therefore it's very hard to predict what the best timeout interval will be. And therefore usually the timeout interval is much larger than necessary. Means it leads to inefficiencies when we lose data. Waiting for a timeout to expire, a timer to expire, sometimes means we spend a lot of time waiting and therefore very inefficient in data transmission. So the next approach is a way to optimize this inefficiency. It's called fast retransmit. We use the same mechanism as what we just covered through in the basic retransmission. Same scenario, 6 segments sent, the third one's lost. B sends back the same ACKs, everything's the same, except there's a different condition that A follows here. A receives an ACK number 1001, everything's okay. ACK number 2001, the first 2 segments have been ACKed, everything's okay. And then it receives another ACK with 2001 as the ACK number. This indicates something's potentially gone wrong. I should receive, from A's perspective, it's expecting to receive 3001, an acknowledgement number. But it receives the same as before, a duplicate of the previous ACK, 2001. Then it receives another duplicate, 2001, saying or giving A some indication that maybe this segment that I sent has been lost. Maybe it has, or maybe it's just delayed in getting there. And then it receives a third 2001 ACK, and then it says, okay, let's assume this segment that I sent, data 2001, I've just received 4 ACKs with the same ACK number saying that B hasn't received this segment. Most likely it didn't get to B. Therefore, let's retransmit it now. Retransmit that segment, receive the ACK, everything's okay. The difference between these two, in the first case, we retransmit after the timeout expires. In the second case, we retransmitted after receiving the third duplicate ACK, or the fourth ACK with the same number. This is the first duplicate of this one, the second, and the third.
So the timer is the duplicate. It works like timer.
The third duplicate ACK triggers a retransmission. Or a timer expiring triggers a retransmission. Two triggers now. In the basic mechanism, the only thing that causes a retransmission is the timeout. In fast retransmit, there are two things that cause a retransmission. Timeout or receive 3 duplicate ACKs. Whichever one happens first. In many cases, this will happen first because usually the timeout is quite large. This is more efficient than waiting for the timeout because we get to retransmit earlier. So that's the optimization of the retransmission scheme. And in practice today, TCP uses this scheme, and note that fast retransmit has both retransmit after 3 duplicate ACKs or after a timeout expires.
Like, how do you know that it's 3 acts?
So the 3 duplicate ACKs is defined. That is, it's a number that's chosen for TCP. The idea is we send this segment. Maybe it gets delayed. So it's a chance that this segment was delayed and it arrives a little bit later. Receiving 1 duplicate ACK, maybe it was just delayed a little bit and we'll eventually receive the ACK later. Receiving 2 duplicate ACKs means, okay, there's a more chance that it wasn't delayed but it was actually lost. Receiving 3, we think we're highly confident that it was lost. Not 100% sure, but it gives us increased confidence. If we receive 4 or 5, even more confidence that it's lost.
So 3 is like for every network, or
3 is the defined mechanism, the standard. Yeah. It's a reasonable trade-off between not waiting too long and being confident that it was lost. So we retransmit earlier and therefore can be more efficient. What occurs first, timeout or 3 duplicate ACKs? Always? Not always. It depends upon the time at which it takes to get the ACKs back. If it takes a long time to get the ACKs and our timeout interval is very short, the timeout will occur first. But in practice, most times the 3 duplicate ACKs would occur first, and therefore we'd retransmit early. So in fact, fast retransmit is included in TCP as well as the timeout retransmission.
and what happens if the first one lost?
First one is lost, then we'd get an ACK saying,
Are we get an act or
not if the first segment was lost, we wouldn't get an ACK for that segment, but the second segment that's not lost, we'd get an ACK for that saying, I'm expecting to receive sequence number 1. If we don't receive the first one, B would send back an ACK saying, I expect to receive sequence number 1. If we lose multiple segments, it becomes more complex. If we lose segments 2, 3 and 4, it becomes harder. And there are further optimizations to handle those cases, but we will not cover them. So that's the basics of error control in TCP. There's flow control mechanisms to prevent the source from overflowing the buffer at the receiver. And there's congestion control mechanisms to prevent the source from overflowing the routers in the internet. The algorithms for flow control and congestion control add more complexity to TCP, and we're not going to cover them in this course.
come on, bring it on.
If you choose Internet Technologies and Applications as an elective, then you can cover more on TCP then. Any last questions?
Before execution.
We have 10 minutes for the quiz. Any last questions? Everyone's excited. Let's start the quiz.